So welcome to part 3 of lecture 19. So we want to kind of focus this part on the question of when can you diagonalize a linear operator? The previous example shows that it can be done. You may remember from Math 1B03 that sometimes you can diagonalize and sometimes you can't. So the question is, when can you diagonalize a linear operator? And there is actually a very nice answer to this question. Okay, and let me just walk you through the description. So say you have a linear operator and you know its eigenvalues, and these are the distinct eigenvalues. Then the following are equivalent. Well, then the operator can be diagonalizable if and only if the vector space V has a basis of eigenvectors. Okay, so that's one way to check. Another way to check is to say that V is the direct sum of all of its eigenspaces. And another way to check is just saying that the dimension of V is the sum of the dimensions of the eigenspace. So let me just make a comment about 3 and 4 to tie it back to what we proved earlier. We have this particular result. We know that this is a direct sum, and we know that we have an inequality. When this is an equal, it means that your operator is diagonalizable. And similarly, you have that this is a subspace of V. You always have it's a subspace of V, but if it is equal to the whole space of V, then your operator is diagonalizable. So that's another way of thinking about what we're doing here. Okay. Now, what we're going to look at is mostly kind of the equivalence of 1 and 2. And let's go back to our previous example. Notice that we found two eigenvectors that act coming from different eigenvalues that formed a basis for R2. So once we got to here, we knew that our operator was going to be diagonalizable. Okay, so here is the statement. We'll prove some of the cases. We won't prove all of the cases. Okay, so let's prove kind of the equivalence of 1 and 2. So let's assume that you have that V1 through Vn is a basis such that the associated matrix with respect to that basis is diagonal. Now we know that because this is an upper triangular matrix, the di's are the eigenvalues. That was proved in a previous lecture. So these are the eigenvalues. So whenever you can get the associated matrix in upper triangular form. So just remember what this means. So this means that t evaluated at vi is the same thing as multiplying the vector by the constant di for each I. But when you look at this expression, that means each vi is an eigenvalue, or sorry, an eigenvector. So each vi is also an eigenvector. So v1 through vn is a basis of eigenvectors. So v1 through vn is a basis of v of eigenvectors, which is what we wanted to prove, that the vector space would have a basis of eigenvectors. So that proves the statement 1 implies 2, and let's look at the second statement. 2 implies 1. Suppose that we have a basis of eigenvectors, and maybe here I'll put the vector space V. And so what we know is if I move down each of my eigenvectors, t evaluated at vi is the same thing as lambda I, maybe I'll write it as lambda k times vi for some lambda k in my collection of eigenvalues. I'm not exactly sure how they all get tied up. I know each of these gets associated. Each of these v1 through vn are eigenvectors. When I multiply it, I should get a scalar multiple. And so this scalar multiple should be one of my eigenvalues. But now, what that means is that when you look at the matrix MT, right, and you look at the ith column here, what you get is that in the ith column, you will get lambda k in the I spot, right? So you get, here's the I spot, and this is the ith, maybe this is the ith row, and this should be the ith column. Okay, and this is true for each I. So anytime you hit anytime you hit a diagonal, you get one of the lambdas, and every point off of the diagonal, you're going to have a 0. And you're using the fact that this particular fact right here that I've underlined. Okay, so the DI, so this is a matrix, this is a diagonal matrix. So this is a diagonal matrix, which is what we wanted to prove, right? So this proves the equivalence of T and V being bases of eigenvectors. The equivalence of 3 and 4 actually are followed very easily. If this is a direct sum, then the dimension of V is just a dimension of each of the pieces making up the direct sum. This is kind of going back to chapter 2 and chapter 3 material, and same way vice versa. If you have this equivalence, if the dimensions are the same, then you have the vector spaces should be the same as well. So 3 and 4 follow easily, and you're going to have to go and look at the text, where the textbook will work out all the details showing you that these two things are the same. Okay. For the interest of time, I kind of skipped the proof here. And I thought it was more informative to see what the equivalence of 1 and 2. Okay, so that proves the theorem. And let me just kind of state one consequence, which is something we use actually in Math 1B03 a lot when we did examples, is if we have T being a linear operator, and if we know that the dimension of V is n, and if we know that n has distinct eigenvalues, then T is diagonalizable. So this is something that we used in Math 1B03, is like if you could show that each of your eigenvalues were distinct, then the procedure to find the diagonalization would always work. And so the corollary proves this. I want you to think about this, and in part 4, I will prove this, and we'll have some concluding comments and some interesting observations.